typically you start with these sort of you know atomic cases, and then build up from that. Okay.
Physics has warped me, so I can only see these as point charges.
Yeah, that's fine too. I mean, it's it's the same idea essentially. Okay. Yeah, especially for Laplacians. All right. So how do we put this all together and solve for boundary value problem solutions using Green's function? And let's do this on the ball. So I think I maybe, just enough time to work through this. Okay, so let's assume the following, that we have a homogeneous PDE here, just the Laplace's equation with an inhomogeneous boundary condition. Okay. So we talked about this a while ago, and you can essentially, using the solution to Poisson's equation, right? U of x is going to equal just the integral over the surface of the boundary of your boundary condition integrated against the normal derivative of the Green's function here. Okay. Well, now we can actually get what that Green's function is and compute that normal derivative. Okay. And what we'll find is that we should recover the Poisson kernel. So we're going to try and converge back to the Poisson kernel solution that we got by using separation of variables, using some geometric series, and then extracting the Poisson kernel. Presumably, we should get the same result if we use the Green's function approach. So this is just sort of a sanity check. Okay. All right, and I may not get through this, and that's okay. We'll finish it up on Wednesday. Okay, so what did we just say? We said that the Green's function solution here, well, because it's a function of the magnitude of x minus y, I'm just going to write it like this. I'm going to just switch the order of the y and the x. Okay. And recall that x tilde here is equal to x scaled by the square of its magnitude. Okay. So then I just have to do a bunch of partial differentiation if I want to get the normal derivative there. So this is going to be the yj derivative of y minus x, the y, of phi of y minus x. This is going to be the yj derivative of phi of x times y minus x tilde. Okay. And what are these things? Well, d phi dyj of y minus x in this case is going to be equal to 1 over n alpha of n xj minus yj divided by x minus y to the n. Okay. And the partial of the reflected part is going to be a bit more work, okay? But we can work it out. So we have, let me write it down here because I'm running out of room. So this is going to be equal to minus 1 over n alpha of n y. Not sure why did I write this? I want this to be yj. Okay, yj x squared minus xj divided by x y minus x tilde to the n, okay? And this is equal to minus 1 over n alpha of n yj x squared minus xj divided by, and because we're computing this on the boundary here, right? So remember that that solution is computed on the boundary. We can just write this as x minus y to the n, y is on the boundary in that case. Okay. So dg dny of xy now is going to equal the sum from j equals 1 up to n of yj dg dyj x y. This is now equal to minus 1 over n alpha of n, 1 over x minus y to the n, the sum from j equals 1 to the n of yj. And now we have all these terms, yj minus xj minus yj x squared plus xj. We can collapse this to minus 1 over n alpha of n, 1 minus x squared divided by x minus y to the n, okay? And if you remember, right, our solution using the Poisson kernel, this should look a lot like what we had in that case. So essentially we have u of x is equal to 1 minus x squared alpha n times n here, integral of over the surface here, g of y divided by x minus y to the n integrated over the surface, right? And so if we were to change coordinates, okay, to polar, okay, essentially reveals this is the Poisson kernel integrated with G in this case. All right. So in that case, we had some R's floating around, right? But essentially we had the same, integration against 1 over x minus y to the n, okay? And then this this additional term out in front here, and this scaling by the surface surface area of the ball that we're integrating with them. Okay. Questions about that calculation? All right. So let me just sum up today by saying, so to compute these Green's functions, the key is to find these corrections essentially to the fundamental solution in order to cancel out the boundary conditions. Once you have the Green's function, you can construct a general solution by integrating against the Green's function or its normal derivative on the boundaries in order to see how that shapes your solution in the case of Dirichlet boundaries. We still haven't talked much about the case of Neumann boundaries, although we did talk about these issues of non-uniqueness in the case of Neumann boundaries a bit on Friday, and you also sort of probably came across this in your homework. So the issue once you introduce Neumann boundaries is that you have an issue of non-uniqueness, and you also have an issue of solvability. So not all Neumann boundary problems are going to be solvable. So we need some additional compatibility condition in order to assure that the boundary value problem you've written down actually has a solution. So that's what we'll talk about on Wednesday. And then I think maybe we're just about done with Green's functions by then, and we'll move on to nonlinear waves for the last bit of the course. Okay. All right. So that's it for today. Yeah, if you have homework questions, you're welcome to stay on. So otherwise, see you Wednesday.
Thanks, Zach.
Yeah, thank you.